Hello everyone, welcome to Group 12's final project presentation for the AI courses. The topic of our group is topic 11, multi-class news classification using Navy Bayes. So in today's digital era, the volume of text data generated every second is massive. The manual classification is simply impossible. Therefore, the goal of this project is to build a complete machine learning pipeline capable of reading raw text and automatically classifying it into specialized topics. So, my team has me, Đỗ Thành Long, as a presenter of this video, and also I got Tuấn Đạt as a main coder of this project. So in this video, instead of focusing too much on academic theory, our group will focus maximally on the technical implementation. We will walk through 8 main sections from environment setup, data processing, and building the model of the architecture, to a live code demo and a deep dive into the model error analysis. So, before diving into the code, I want to briefly review the algorithmic foundation so everyone understands why our group chose this solution. We are using multinomial Naive Bayes. As you can see from the formula of the screen, Bayes' theorem helps to calculate the probability of an event occurring based on the related conditions. In this problem, the event is that the article belongs to the sports topic and the conditions are the appearance of the keywords like goal, ball, or match. So, the key point here is the word naive. This algorithm assumes that the occurrence of the words is independent of one another. For example, it doesn't care if the word artificial appears next to the intelligence or not. Although, although this assumption simplifies the reality of language, technically speaking, it allows the algorithm to calculate extremely fast and effectively on high-dimensional data, something that more complex algorithms sometimes struggle with in terms of computational resource. So let's talk about the technology. To implement this project, the group built it on the Python platform with core libraries. The scikit-learn. This is the backbone of the project, providing all tools from data loading to modeling. The NumPython for handling fundamental metric operations, and the matplot library for data visualization, plotting the confusion matrix later. In detail, we import so many libraries as you can see in the picture here, such as the Fetch Trending News group to load the benchmark dataset. The most important we gotta tell later is TF-IDF virtualizer to convert raw text documents into a matrix of TF-IDF features. Also, we got the multinomial MB to implement the Naive Bayes algorithm for multinomially distributed data. And also the important one is pipeline to sequentially applies a list of transforms and a final estimator. We also use accuracy scores, confusion matrix to evaluation, and matpilot library.pilot Python plot or confusion matrix display to visualization. Regarding data, the group is the standard 20 newsgroup dataset as I told you before. This is a classic dataset in LMP consisting of about 80,000 from forum discussions divide evaluate into 20 different topics. You can see here the list of topics below. From computer, we got graphics, hardware, to science, space, medicine, to politics and religions. But the most important technical points here, right from the data loading stage, the group performed a strict train or test split using the parameters subnet equal train and subnet equal test. Why? Because in the text classification problems, leaking test data or data leakage into the training process causes the model to memorize the answers. This separation ensures that the accuracy we measure later is most honest figure. So coming up with the next part is model architecture, scikit-learn pipeline. Instead of processing data in disjoint step, the group designed a scikit-learn pipeline. This pipeline acts like an automatic production line consisting two main steps. The step one is a feature extraction in TF-IDF vectorizer, and step two is multinomial MB. Look at the detail of the two steps. With the step one, feature extraction with TF-IDF vectorizer, the computers cannot understand raw text strings. We are forced to convert them into numbers. The group chose the TF-IDF method instead of simple word counting back of words. With TF, it means terms frequency, counts the frequency of the word appearance, and IDF means inverse document frequency. This is the beauty of the algorithm. It penalizes or reduces the weight of words that appear too often but have little meaning, like there, is, At the same time, it boosts the weight of four distinctive words like CPU in the computer topic. Result: the output of this step is the numerical matrix representing the text. And the step 2 is classification or multinomial MB. The multinomial variant was chosen because it works very well in discrete count or frequency data. The model calculates the posterior probability for the 20 topics and assigns the label of the topic with the highest probability. Encapsulating this into the pipeline keeps the code cleaner, easier to maintain, and most importantly, applies the exact same processing logic to both the train and the test sets. Go out with the third one is training and inference. This process happens extremely the first phase is training phase. We use the fit method as you can see here. The fit method is it used to AI learn the vocabulary dictionary from the training data and calculate the TF-ID web weights and estimate the conditional probability of the words given in each class. And the second phase is inference or prediction phase. We use predict method to show the workflow is new unseen documents are fed into the pipeline, and the text is transformed into vectors using the learned vocabulary, and the trained model predicts the most likely category. We're gonna show the output later in the demo code. The sixth is performance evaluation, and after running, I got the model accuracies. The result achieved is 77.39%. To evaluate the number, if we guess randomly across 20 topics, the accuracy rate is only 5%, and 70% is a 50-fold improvement over random guessing. This is a very good baseline result. And the challenge preventing 100% accuracy, as you can see here, is the noise, the informal language, typos and headers in email data, or ambiguity in subject matter overlap. However, the accuracy figure doesn't tell the whole story. I'll invite everyone to look at the confusion matrix as you can see here. The vertical axis is the true table, and the horizontal axis is the predicted label. Please look at the main diagonal, the brightest line here. It's very sharp and bright. This proves that the most predictions match the actual labels, especially for sport topics like hockey or medicine, or the model identifies them extremely accurately. So, so this is the part of the group that is the most power. Error analysis. Why didn't the model reach 100%? The group zooms into the noise points some prime cells outside the main diagonal you can see here, and we discovered two interesting issues. That the first issue is confusion in the regular group. You can see here we have 123 articles about the atoms, and that the machine mistakenly classified with Christianity. So technical reason is because Naive relies on the keywords back of words. Both atheists and religious people use common vocabulary like God, Bible, Jesus, belief, and moral. The computer only counts words, so it that cannot distinguish the context, whether supporting or opposing, leading to confusion. The second issue is hardware, the computer hardware group. Similarly, the machine frequently confuse IBM PC hardware than Mac hardware. The reason for that is because both topics talk about RAM, drive, monitor, SCSI. The technical vocabulary overlap is cause of this error. Meditation. Here is our Python script. We strictly define a scikit-learn pipeline named text.cof. As mentioned in the video, this single object is calculates both the ITF vectorizer for feature extraction and the multinomial NB classifier to ensure a clean and consistent workflow. And now I will run the code. First, the fit function trains the model, and yeah, you can see the you can see how fast it is processing over 80,000 documents in just a few seconds. Immediately after that, the predict function runs on a test set, classifying thousands of unseen articles based on the patterns it just learned. And here are the results. We achieve an accuracy of 77.39%, as we showed before. And also we got a confusion matrix as the confusion matrix.png here. It just generated. This visualization confirms that while our model is highly accurate for distinct topics like sport, it still faces challenges with semantic overlap in regions and hardware. And you can see here the most common misclassifications with analysis in a detail list where I use two for loops to comparing the new group test target names. They similar with each other, and the number of the common equal than 0, and I freeze out the list. That's my debug code here. And to summarize, through this project, Group 12 has successfully built an automatic new classification pipeline, and also we demonstrate the speed efficiency of the naive Bayes algorithm, and most importantly, clearly understood the nature of the semantic ambiguity in natural language processing through error analysis. That concludes our group's video. Thank you everyone for your time and watching the video.